We study how to make imines and enamines when we use nitrogen nucleophiles. So now, from that point, we can do other things, functional group interconversions. Let's say that I have cyclohexanone and make it react with hydrazine. In hydrazine, remember, this is similar to a primary amine. You see that it's like the R is one of the NH2. Okay, so let's do the ideal pH. So you will see likely this on a question. pH between 4 and 5. Let's do this. Under that condition, we know that we will form an imine. And the imine contains a double bond with nitrogen. And now an R group, which in this case is NH2. That is a hydrazine. And that is, the product is called a hydrazone. What is interesting about that compound when we make it is that we can reduce altogether the carbonyl group to the corresponding alkane. In other words, we can eliminate that. This reaction, I'm not going to draw the mechanism, but this is called the Wolff Kishner reduction. Okay, and again, it will reduce this to the corresponding alkane. So for that, we use KOH, water, KOH, water. We will use also heat. This is what's happening. So it reduces completely to the corresponding alkane. And it produces nitrogen gas. So this reaction goes all the way to product formation, because again, you're forming a gas that is liberated, and the reaction is irreversible. That's the alkane. So cyclohexanone. Okay, that is a useful reaction. Another thing that we can do with imines is what we call the reductive amination. And so, let's see. I'll say that from cyclohexanone, I'm going to make it react with another primary amine. And I'm doing RNH2, a primary amine. We know that acidic conditions, we will form an imine that will have a double bond here and an R group. So remember that. Double bond with the nitrogen in the R group. And so that is your imine. And here we can do another functional group interconversion. The Wolff Kishner allowed to go from the ketone to the alkane, or can also be aldehyde to the alkane. Now here we're going to go with from the imine to an amine. In this process, this reaction is called reductive amination. It is another reduction, but in this case, we will use a hydride that will reduce selectively imines and enamines. And that is, think of, here we have sodium boron hydride. Sodium boron hydride. Remember that we can use product solvents with this, such as methanol. That's where you use aldehydes and ketones. Now we're using a different hydride. We're going to modify the sodium boron hydride, and we're going to change one of the H's by a cyano group. So it's sodium, and now I'm going to have 3 H's and a cyano group. This is selective. I will reduce selectively imines and enamines. So let's draw an enamine. If I had an enamine, the enamine, remember, is this R and R. So enamine, and this is an imine. Starting from the imine, you're gonna get the following. So this is reduced to the following. So that is That is an amino group. It should be reductive amination. I just wanted to that H. So notice that is an amine. And that amine is actually secondary because you have the amino group and there's the R in the cyclohexyl. If we do that with the enamine, so I'm going to use the same reagent. So the modified hydride, we're going to reduce the enamine this time to a tertiary amine. So it will be N, R, N, R. So that's another useful functional group interconversion from imine or enamine to the corresponding amines. So in a later video, I promise that I will make one about all of the reduction reactions of carbonyl and in what conditions we can do that. But here in this chapter, we have these two important reductions. The Wolff Kishner to remove the carbonyl, so the reduction completely to the alkane, and the reductive amination. You're making the imine or enamine, and then you're using this reducing agent to form secondary amine and tertiary amine.